for the base. And still expert in meteorology and data simulation, and trying to learn about this. So, this is the presentation.
Yes. Thanks for inviting me. And as I said, I work in data forecasting. We have a European center in Reading where every day we collect several times a day, continuously all the satellite data and all the observation data for the ground in real time. Then we make merging of all these data with our forecast from yesterday, make forecasts up to 10 days ahead and even longer. And this includes atmospheric waves and once a week also do for the ocean. So I think there are quite similarities between what I've seen between what we are doing here in solar physics and what we were doing a few years ago. So this is the outline of my talk, and the talk that I'm giving today is a very, very practical one. Let's say, what are the components we need? What's a fruitful approach to combine observation and models? Given that we have some observations and some models, we want to know something more either for predicting or about your model itself, or about the physical processes which your model is trying to describe. We are trying to use the observational information to help you. So, let's just see what do we do if we want to combine models and observations.
Pointer?
Well, yeah, I pointed my finger, but I think it's a very nice screen. I don't want to. There's a point. I didn't wash my hands this morning, but you know. So, there's a little nice picture which really explains a lot about the situation where we are in meteorology today, in atmospheric and geophysical sciences. So we've got two things, and you could try to make a mapping here while I'm talking between the situation in solar physics and meteorology. If you feel you want to give us a feedback,
we have no boats on the sun.
That's a good point. I mean, that's. I know you have satellites, so that's at least that's good. So we start with models. So in meteorology, when we're doing weather forecast, you of course got the atmospheric model, but of course the atmosphere interacts over 7/10 of the Earth. The ocean has lower boundary conditions, and for the ocean we've got sea surface temperature as a very main driving variable. We've got ocean models. We've got for the boundary condition we've got the separate model, which is a ocean waves model. Describes the friction of the lower boundary on the atmosphere, and also how the atmosphere drives the waves. Over land, we've got a similar thing as over ocean. There we've got different types of vegetation, etc. They describe different types of interaction between atmosphere and land. You can imagine there's a different condition over lakes, over forests, etc. So, even in the atmosphere, we have some atmospheric chemistry and aerosol models. So what we have here is different component models which are coupled together weakly or strongly, and with one or two-way interaction, usually in such a way that the flow of information is from more certain models to less certain models. So, for example, the atmospheric model is quite well understood. Some aspects of the land surface model may be less well understood. So, if you have a coupling between the two, you would tend to have the coupling from the atmosphere to the land surface model rather than all the way around. Then, that is our models, collection of models of different sophistication, all coupled together. then with observations, we get a lot of observations, and the main characteristics of the observations is that they look very different characteristics, measuring very different variables. Sometimes they're not even measuring something which is explicitly described in model, like satellites. Okay, some measure movements of clouds, but the most important observation in our systems, the two most important. One is the one when we send up balloons, which actually gives a vertical sounding of the atmosphere. But the other most important one is just from satellite, which just receives radiation from the Earth, and so it just we get one value, brightness temperature, or radiance, and you're trying to say something about the atmosphere from that number, and then given all this heterogeneous information, we need some kind of a rational approach to combine all this together with models. That's a little bit what I'm going to show you today. This is just what I want to show you, that when we start to do this, which I understand is different from what we have in solar physics now. In solar physics you have too little observations. We have actually too much observations. Well, let's say we have a lot of observations, but they're not always measuring exactly what we would like them to measure. Sometimes it's difficult to measure what you would like to get at, and I think that's the same situation in your field. But you can see here, this is what we're trying to merge together, all this information. From satellites, you can see it in tracks, from ships, and from all different kinds of sources. It's irrelevant what the sources are. You see it doesn't look homogeneous.
What's the difference between blue and red?
I'm just showing you,
Top left.
there's these different types of land surface observations.
It's communist and
Yes, so it oh yeah. Actually, this may be down to the type of instrument. This is also reality that we start out in the beginning, you have maybe just a couple of different types of observations. As time goes on, more and more satellites are sent up, and you will have the same development in solar physics. More and more instruments will start to observe the sun, and they will all look different. And for each of these observations, you will have to learn to understand what is this observation really measuring. So you can say that as time goes on, we go from maybe 1, 2, 3, 4, 5 different types of observations to order 20, 30. And for each one of those, you basically need one person to full time to try to understand this. How you map the information from this observation to your model. That is one aspect, that we get more and more complicated observations. Other aspect is that we just get purely more and more observations. This is like in millions per, these are the use observations in millions per 24 hours. So we go from 1996, this is when I started to work at this European Center. This is the situation we are getting today. So they're like a couple of orders of magnitude. And this development is going even faster. And notice we are only using about 5% of the data because much of it is redundant. This is a good, you need to have a robust system because one day a satellite will fall out of the sky and you don't want to be completely left at the mercy of one satellite, for example. But anyhow, this is the situation. So what I want to say is
it's a jump between 2006 and 2007. What happened there?
There is a new instrument from a satellite, new infrared high resolution infrared observation set that comes in there.
It's not much data. It's only 30 million 24 hours.
Well,
if you make images, one image is, or count images, one data point, or each pixel in the image.
Yeah.
Yes, each pixel in the image is one
The
data
image
point.
is the data.
Now, you want to multiply this with a factor 20 to get the real number. This is what we use. Multiply this by 20 to get to 6 billion. 600 million.
I mean, it's true what Sasha said, that it depends if it's just a point on a given map that you consider as a data, or if it's a map that's as data.
No, it is a point. I always think it's for me, observation is the smallest useful bit of information. Well, there's one exception to that, but that's okay. So this was a little bit. What I want to say with these pictures is that as time goes on, things just get more and more complicated, and one needs to have a systematic approach to things. Something which is generally flexible enough to cope with any type of observations. And for example, the naive approach, which we started with in the 70s, you got a model, and you just replace the model values by some interpolated observation values at initial time and integrate forward. That gets you somewhere. It's better than nothing. You get much better. And that approach doesn't work. For example, for this, when you're measuring radius, there's nothing in the model that says radius. In our models, we are working with wind, temperature, and things like that. Anyhow, so let's go through the basic concepts and how we go around to combine models and observations. It's very straightforward. So what have we got now? We've got a model, m of x. M is a nonlinear model operator. X is the state. This operator is active 1. In our case, let's say just the atmosphere. We've got observation, given as a y, observation vector, which is a collection of all the observations we have of our state. It can be direct or indirect. And a very important concept, we got some what I would call a first guess model state. And the jargon we use for that is just background, XP. And that is just the fact that you have somewhere to start from. Your model doesn't start from 0. When you start the integration, you put your observations into your model, you're not starting from total ignorance. You have some idea, at least a mean state. And of course, when you repeat this process in time, over and over again, your initial state you start from gets better and better, so it is already quite good. So, in meteorology, for example, we had a situation that yesterday's forecast is a very good indicator of today's analysis. 90% plus of information is already in yesterday's forecast. There's a few percent, which every day this keeps it on track, actually.
And you speak about global modeling or just prediction of parameters like velocity, temperature distribution?
Yeah, this is applicable to any model, of course, framework. I'm just talking abstractly in terms of model observation. But of course, when I'm always talking about, in general, a global model describing all the relevant parameters of the atmosphere, with what we need from the surface of the ocean and things like that. So, but yeah, sorry.
Let me be really pedantic and ask you. So in this model you have some variables like velocity, temperature, pressure.
Yes.
And you have some parameters like viscosity.
Yes.
And maybe, so.
Yes.
What you are trying to, so the parameters are basically remains fixed over your whole evolution. They are not changing. Or even when you are trying to assimilate the data, you are not changing the parameters to assimilate the data.
No, we don't change parameters.
Excellent.
Except what is the prescribed time-dependent evolution of the parameters, which we know from physics or other, like day-night differences, the irradiation from the sun on the surface. That, of course, is a daylight cycle, depending on the rotation of the
The question is, can you also make sure that maybe some conservation laws are followed by your...
You can, yes. It all depends on how you write your equations numerically, and they should conserve some energy and other things, momentum. So, now, two very important things. We have models, we have observations. First concept is each of those components has errors in them. they're not perfect. And in particular, observations and observation errors, we know that. And we know also that this first case, or this background state we started from, that's not perfect. It has some errors which are maybe spatially correlated, but they're not perfect. And even the model itself has errors in it. We don't have perfect models. So that is very important. The second thing is that, as I said, observations can be indirect. So what I would like to do is, instead of using the observations to describe things, let's use an observation operator, which is a operator which takes you from the observed quantity to some recognizable model quantities. Give you two very quick examples. Very simple observation operator. For example, wind. You measure, or temperature. You measure temperature in this room. The resolution of our model is maybe 25 by 25 kilometers, grid points. So this measurement is some distance from the closest grid points. So the observation operator, sorry, this should be x. Okay, put an x here. This is wrong. Just, yeah, I think this just fell down here.
No.
Up there. Because so this is very important. Okay.
No, it may be right. Your
No, no,
observation
no,
is
no.
a y. So observation operator should actually act on y.
No, that's where I'm coming. This is completely wrong. So put this x here. So what I'm saying is that we want to have something to compare with this observation in this point, so that we interpolate from a neighboring model grid points the temperature in neighboring model grid points to this particular point. This is a pure interpolation. So in that case, the observation operator is interpolation for the model to the observation location.
But in principle, model has some empirical constants, and you use observations in order to verify these constants.
No, the
Or-
constants are being held fixed.
Now
Sorry?
you
The
are right.
constants are being
The
held fixed.
constants included in
not
background
the fixed.
parameter. Yes.
I mean, I don't speak about the constants like viscosity or other things, but there are, every model atmospheric has empirical constants.
Yeah. So you're very right, and this is two parts. So that what you're describing now is part of our research. We do our research before we do our assimilation. So part of our research and development, we come up with the best description of our parameters. We mostly do not try to estimate our parameters as part of the process of combining observations and models. We have already found, let's say, a best estimate of our parameters before we do the forecast. So that's how we do that. That's a part of the research process.
Any parameterization has empirical constants.
Yes, yes.
But
Okay.
in this they're holding fixed.
So this is the thing. And then another very important example of observation operator, this is really central, is that from satellites you measure something. You may measure magnetic field, we measure radiuses from coming out of the atmosphere. And in our case, for these radiuses, each radius is measuring a certain wavelength and maybe different polarization or whatever. And then we have a radiated transfer model. This takes the column of the atmosphere, all the model variables in that column of the atmosphere, from the surface, including the surface condition, up to the top of the atmosphere. We integrate this forward with a radiated transfer model. In this case, our observation operator is something which relates one number, the observation at the top of from the satellite scene, with the whole column of model values which it penetrates, including the surface condition, or clouds in between.
Excuse me, this operator can describe, for example, profile of temperature in this column.
Yes, it includes the profile of temperature, and it takes this temperature into the radiated transfer model, calculates the radiuses coming out of the atmosphere for this particular wavelength. So that is a very important link between observations and models. So now we have this is a very fundamental framework, and it links This is how we think about when we have observations, models on one side, the map between two spaces, between observation space and model space, and the observation operator is the key thing between the two. And given this, we want to find the best estimate or analysis XA of the state. Given that we have the following information, we have some background, XP, that is some estimate of our initial state. We got our observations for a certain time interval, 0 to tau. We have collected them over some time period. And we got this here. So if you describe the system, we got the model evolution. This has some errors in it. We got the initial condition here at time 0. Well, we had some first estimate of it. But that of course has some errors in it. And we got observations here. During this time period we collected observations. Some we call it time window or data separation window as well. We call it time period. And each of the observation, these big N observations, has an observation operator associated with it. It acts on the model state and an associated observation error. Now, to solve this, to get where it is, the first thing we have to ask us, what are the characteristics of these errors? What is the PDF probability distribution of these errors? Because now we are, I mean, what we teach educated students in physics is of course to solve this part of the problem. We've got this 0 and this 1, so it's a pure initial value problem. And then we add these complications and we get the link between observations and model. We can solve with some kind of a minimization algorithm. Because we don't have really a straightforward solution to that. So this is the start. So how do we do this?
Statistical errors, right? But also systematic errors.
We consider those also. Yes. It's very important to consider systematic errors also. I'm just going to go through statistical errors here, random errors. But I can show you where I can just indicate where we will put in the systematic errors.
So the time evolution is actually embodied in M of X.
Yes. That is just model evolution. And what I'm trying to do now, just to illustrate, what I'm trying to solve now is that green is always a thing you don't see. It disappears, okay. So what I showed you now, just to be clear, this is time. From 0 to tau. We got some observations here. Y1, Y2, well, let's call it Yn.
And the vertical axis is a y, or what?
I'm just going to take the vertical axis is state. The multi-dimensional state, some state vector. And we have a starting condition here. So you call this is x or state. We have a starting condition here, xp.
Xp is initial conditions? Or what?
Yes, this is our initial condition, what I call it background. And then what we're trying to, yes.
The dimension of y and the dimension of x are not the same.
Exactly, they're different spaces. So,
So typically y is smaller than x.
can be either or. In oceanography, for example, we have less observations than the number of model dimensions. For example, in meteorology, it's the other way around.
Will not that make the problem over-determined?
Sorry?
Will not that make the problem over-determined?
Yes, that's why we need to do minimization to solve this. You cannot solve this analytically. You have to do the optimization algorithm. So what we're trying to find now, I mean, if you could just start a normal focus from this, let's say we get something like this. And what we're trying to do now is we are trying to combine this information here with our model evolution and observations to try to get closer to observations. So in the end result, when we've done everything, we may end up with something which may look like this. We may have changed this a little bit. We may come up with something like that. And the hope being that a forecast going forward to this state is better than what it had originally. Which in most cases is true, fortunately, if one does it correctly. Sometimes it doesn't work, as you have noted when we get the forecast wrong. Okay, so far it's just the basic concepts. So what we need to do now is to combine things together, and simply what they're looking for, given this statistical information, they're looking for the most probable solution, which in most cases, there are exceptions, but in most cases is what is the most sensitive thing to do. I mean, you wouldn't want to go for the least probable solution. So,
the left-hand plot, when you said x, you probably actually mean h of x, yeah? And then it's y. It has the same space as y.
is that the confusion? Yes.
Is that, should x be replaced by h of x?
No. What I should do here is that when I'm comparing the two, I calculate actually h1 of x here. And I calculate h2 of x.
Right.
And that is the one which communicates between the two. So, as a part of the book, I do calculate those to compare the two. Because just to go back to your questions, the dimensions of...
so h of x has dimension of y.
Yes. So dimension of... No, actually, the dimension of this y vector here, is just... it goes from 1 to a number of n observations. X... That is just, let's say, a discretization times the number of variables. So, basically your vertical horizontal resolution times the number of variables. Or if there are some variables, it's a two-dimensional, one-dimensional, the other one. This.
There is some connections with equations, of course. In model you use equations. X is variables in this model, like a temperature, velocity,
Yes.
And concentration.
Yes.
H is nonlinear operator which enters in the nonlinear equations.
No.
Like equation for the evolution of tuning energy,
Observation
or
No.
mean temperature, mean velocity.
No. H is something which gives you observation equivalent.
Observation equivalent.
Yes. The
Like
model's observation equivalent.
Like temperature in one point.
Yes, exactly. You need to interpolate the model from the surrounding point to get temperature at one point.
Okay.
That's your observation equivalent of the model.
Okay, so you have output from the model,
Yes.
just temperature field,
Yes,
and you have points of observations.
exactly.
Okay.
And then, so
Okay,
so you see here, H is the communication link between model space and observation space.
Let me ask you a really stupid question. Say
No
you
stupid
have-
questions, only stupid answers.
Say you have temperature at several grid points,
Yes,
temperature as your observation,
yes,
and you are evolving your temperature.
yes,
So you can interpolate from your result of your different PDE
yes,
to actually find the temperature at the observation point and compare them.
yes,
Now assume that you also were evolving pressure,
yes,
but you had no pressure observation.
yes.
So then basically you couldn't compare them in any way.
Well, not directly, but the link there is a model. Because when you do forward integration, if you measure temperature, that of course affects density, and that will affect your pressure. So it's the model is what links together the different variables. That's a very important point actually. Could you point that out now? You can just repeat that later on. But you measure one quantity, like temperature. That gives you information on wind actually, through the model, through the balance in the atmosphere. You got thermal wind, you got So this called geostrophic wind, which means that if you change temperature, the wind has to make some inflow to compensate for that. And these balances which we have between the different variables are essential to do data simulation, because that is the link which, for example, in this background state here, that when you do your analysis, that is what gives you, what transports information from one variable to the next. That there is some correlation between them through the model. Okay, but we can go through that several times. Okay, so but what we want to do, we given our observations, given our background, and we got the PDF here, or the probability in this case, of our state given these observations in this background. We want to maximize that. That is our analysis. It's as simple as that. There is nothing more to it. Then all the rest is just implementation details, really.
Maximize with respect to what?
Uh,
Which of the variables are maximize?
Probability. Maximize with respect to probability. So you have to maximize the probability. To maximize the probability, you have to have an idea of the probability density function. That would be the, and we are talking about the maximum likelihood method, that would be the most probable state, that would be the top of the PDF.
Yeah, but in practice, what are you doing? You have output from the model, temperature field or wind profile, you have measurements. So after, if there is disagreement between measurements and output of the model,
Yes.
you correct the model.
Yes.
So you correct, what you correct in the model?
We will come to that.
Ah, okay.
It's just very. So going back, so probability is not very convenient to work with PDF. So we just take the log of the PDF. And since log is a monotonic function, that's the same thing here. And I just want to introduce a concept here that instead of saying that we want to maximize probability, we minimize something which we call a cost function, which is just log of the probability. Which is a concept we have. It is very practical because our PDFs, for example, if they are Gaussian, e to the minus x squared, if you take log of that, you just got x squared. That's more convenient to work in that way.
That's like the Hamiltonian of statistical mechanics, right?
Yes, yes.
Alternatively, you can minimize the discrepancy between observations and model predictions, right?
Yes.
Observables for some squares.
Yeah, yes.
Why do you probabilities here?
Well, that because there's also, this is a framework. There's always a one-to-one correspondence between the implied probability distribution and the way you write your, let's say, cost function for your problem. If you say you want to minimize squares, you actually imply that your probability density function is Gaussian. There is a one-to-one correspondence between the two. But actually, to be honest, it's not very fruitful to go further in the probability density function framework. It's much more fruitful to go back to, let's say, minimizing the sum of squares. And that's what we get by this cost function. I'll show you that in a 2 slides time, yeah? So, we want to minimize this cost function. And variational assimilation, that is what that is about, minimizing this cost function.
So that is needed in order to obtain your X of A.
To get our analysis, yes. Because all we're saying here, we want to have maximum likelihood solution. And this is very general for all data simulation. You want to have analysis as your most probable solution given the information you have. It may not be a correct solution, but you don't have more information than that. And we have another theoretical framework which has been used for this by statisticians, which is nice, that is using the space theorem. That is just something which works with conditional probabilities. And what we're saying here is that let's say, working all this map between, let's say, if you want to get most proper state given your observations in the background, that state is equal to getting your most proper background and observation given the truth or whatever that is. And you get this equality. I mean, this is just very, very, very basic from statistics, that if you move this up here, you can see that there is an equality between the two. Okay, but the main thing which I want to get down to here is that if observations and backgrounds, if PDF observation and background are independent, which they mostly are or can be made. I mean, there's no reason to believe that your model integration is in any way correlated with observation which you have from satellite, except if you're using your model as an input to deriving the satellite observation as part of the observation operator. That can happen. But in principle, if these two are independent, then you can write this as a product of two probabilities. And cost function becomes this sum of cost functions for the observation and for the background. I'll just show you very practical on the next page where you can see how this ties up. I mean, if both are Gaussian, then of course you know that you can write and they're independent, then the exponent of the joint Gaussian PDF is just a product of two terms. You take log of that and get the sum of these two terms. Log of e to the power a times b is just a. Okay, so where we are now is this maximum likelihood approach doesn't really assume that you have any particular PDF. But so I hope I can show you later that it's a very, very practical case. If your PDF is Gaussian, and it's not as a severe restriction as it would appear. If it is a Gaussian, you write it like this, then the cost function will look something like what we have down here. And B in this case is a matrix of background error covariances, and R is the observation error covariance. And the way it works is that B is very large dimensional. If this is B equal to, let's say, if you've got a few variables, for example, this is variable 1, variable 2, variable 3, variable 4, 1, 2, 3, and 4. Then, of course, for each variable, the whole dimension of the model space is along this axis here. And then, so this would describe the correlation between this variable at each point of the model. This would correspond to the correlation between this variable and the next variable at all different points of the model. You see that the dimension of this is number of variables times the dimension of the model squared. It becomes very big. So in practice, when we solve this, we try to do some block diagonal approximations. Yes?
You obtain this matrix, or you could obtain it through model calculations, I suppose.
Yeah.
So you run a huge sample of models to populate this matrix, yeah?
Yes, that's what we do. It would be nice to, I mean, one very practical way how to do this is that very simple approach that you can also use. I mean, there are two basic. One is that you make two forecasts of different length, is valid at the same time. You take the difference between the two, x1 minus x2, and you take that as a proxy for your background error. Because background error, in this case, B, that is of course just the error in your initial state. And your initial state, when you are doing this sequentially, your initial state results in a short-term focus from your previous state. If you are repeating observations over a long period of time.
But X1 and X2, this is two predictions for two different models, or
It can actually be
at the same time?
Same model. It can be the same model,
Same model?
but from different time. This could be, for example, T1. This could be from 2T1.
Different time.
Yeah. Yeah.
Different moment in history.
Yes, different point in
Okay.
history. And of course, the difference between those and this is that between this point and that point, we've got observations coming in.
Yeah.
So there are other approaches, but this is how we then go around populating this matrix.
So this matrix B,
Yes.
it changes with time.
Yes. Principle, yes. You can, what you can do, you can take, you can make, in practice you make the largest part of it static, and then you, let's say the leading dimensions of instability, you try to calculate
And same about
Okay.
R.
R is pretty much static. R is most of the time in practice you assume, and it's not, it's a big restriction, you assume the observations to be uncorrelated with each other, so R just becomes a diagonal matrix.
When the elements of the diagonals are constant in the function of time, or
It depends on your model of the observation error.
but so how do I find out R actually?
That's a good point. That is, you need to do research on your particular observation type. So this is nothing which you can do from theoretical considerations. You measure with a satellite. You need to get the values out of it. You need to compare them with something. So this is the whole study. How accurate is an observation from a satellite of state?
Okay,
So-
so if I measure temperature, say,
Yes,
and somehow I know that my instrument has an accuracy up to 3rd place of decimal,
yes.
then my R is something like 0.009.
Actually, R could
I mean, one element of R
yes,
would be something like 0.0009,
yes, for example.
plus minus.
Yes. So this is, but I can describe this in more detail later, but very important point at this to understand is that to get anywhere with whatever approach you want in data simulation, you need to know your error. And that is exactly what you said. You want to know for each observation, what's its approximate error mean? And you want to know for the initial state to start from, how are its error, how are they correlated in space and things like that. You need to know this, otherwise you won't get anywhere. Yes.
If you took as an example, and maybe we will come to that, the Lorentz attractor,
Yes.
then it would be a 3x3 matrix.
The Lorentz attractor would be a 3x3 matrix, yes.
And now this matrix is time dependent. So is that right?
No,
It's actually a fixed one?
I think the Lorentz system is.
Actually, it's both yes and no. Because duality, that's what we like in this world. See, in practice, you can, from statistical consideration, running a very big sample, find this is the mean error. Now, but of course, we know that the error on our initial state at any given time depends on what history. Like it depends on the observation we had in the previous cycle. Let's take an example. We had no observations in the previous time instance. Then the error grows. So the background error will be larger. When you have got observations, let's say good observations, there the error went down. So if you take this to a 2D or 3D field, then you will see that where there have been some observations, the error has reduced. Where there have been no observations, the error has continued to grow through the nonlinear chaotic behavior of the system.
And how do you estimate this error? By something like this, that by evolving the model from two different histories?
Yes, you can do that. There are many ways of doing this. And one way is, if you want to estimate this, is that you can do it in ensembles. So you have, let's say, several different model realizations. These are all running, you're running, let's say, several assimilation systems independently. same model, or you can use different models. Use this same model with a little bit of perturbations of initial conditions and observations. Then you get to slightly different realizations of your initial state here.
Yes.
And you use the fact that the variance of this is large, then you have large uncertainty in initial conditions. Where the variance is smaller, you are more certain. The variance is bound to be smaller if you have a very dense observational coverage, it's very restricted initial state, than if you have somewhere where you are not that certain.
So this error is estimated from looking at the variance of x or xa.
X. You start with XA. The point here is that you make an analysis. XA, your analysis error, has you've been successful in reducing your error in some regions, not in others. Then you integrate forward from this, and of course, where the XA where the error of analysis is smaller, most of the time you will have smaller. I mean, the downstream evolution from that will lead to smaller errors. Okay, but we can get into the details of this.
Can we create a mean of the probabilities in suppose we have some heterology measurement of 10 people.
Yes.
So how to determine background model?
Well,
the probability of the background.
well, the simplest, I think, the trivial example is you've got xp here, you got y there. Let's just work directly with log of this. I have difficulties in.
So the first, the first probability is upon the x. You don't have models here, right?
Yes.
Line. It's only the state.
Yes, but if you know nothing about state, it is equal probability of being everywhere, I would say. If you know a priori information.
Oh yeah, I know error in my temperature measurements at each point
Yeah.
on my map.
Yes.
And then what would the probability of this state? How to determine this?
Well, maybe this. I mean, this is what you start with. You've got an observation error. This is the PDF of your observation error. That is this. Okay. So that is this is PDF of having an observation. It's this is actually observed value, but let's say let's call this is P. Having an observation given the truth. The background.
So that essentially comes from the accuracy of your instrument.
Exactly. The background may have different PDF. This is P of xp to x.
And this is accuracy of model. Yeah? XB.
Accuracy of your model integration.
Yeah, of course.
Yes.
Maybe
Accuracy of
call
your
this
predictions.
should you call this the degree of predictability of the model?
You could call it that, yes.
Because, of course, not the, I mean, if you had a Lorentz attractor, you would not be able to predict everything you want.
No. Now, well, let's just get one thing very clear. That we may get this wrong, we may get that wrong. That's the nature of statistics. So, we may have some measure of predictability, we even get that measure wrong. So, it's like, I mean, we don't know how to predict predictability.
I think it is predictability not in the usual sense applied to the Lorentz attractor. It's in the usual sense that unpredictable nature comes from the nonlinear part. But here the unpredictable nature is coming from the accuracy in measurement. So it's not exactly the same kind of predictability.
But you could propose
If you had a
actually.
linear problem, then probably the uncertainty in the initial condition would have grown linearly or algebraically. Because we have a nonlinear problem, probably the uncertainty in the initial condition will go exponentially.
Exactly.
And so there are two sides to the predictability possibly.
Yeah, you got that illustrated in this and that part here. And in predictability terms, just to illustrate that, I mean, even as a bit of a side issue, here what happens is that you grow exponentially and then in practice you saturate. That's what happens.
We can estimate unknown errors in observations. Because known errors of observations, we know during process of some calibration compared with other measurements, but
let me say a concrete example. Say you have no pressure measurement.
Yes.
Then how do you estimate the error in pressure? Right? That's the same
maybe
question.
yes, but I speak just about if you have measurement of temperature, for example. We know error of this instrument, but in real situation we know just part of this error. But some errors we don't know about this. I speak just about unknown errors in measurements. We can estimate this or just.
Well, I think the pragmatic thing is one just need to be on the conservative side. You need to overestimate errors. It's better to overestimate underestimating errors is a very bad thing. You lead to convergence problems in your analysis. So just factor 1 and 2. Factor 2, that will be fine. 50%. Okay. Now it's okay, but let's just get on with this. Your example, Sasha, there. You combine the two, you end up with something like that. XA combined with 2, you end up with something like this. XA. Actually, to be really fair, the variance of this will be smaller than either of that, so it will be somewhere like that. XA. That's how you combine the two.
What is your horizontal axis?
Oh, that's just again. Let's say, so your state. You got your observation. You got your. Let's just go. I'm mixing the spaces here, but just for illustrations, you can assume that the observation space and model space are the same. The temperature in this room, and then observation, background. Each has their own PDF. Do analysis, come up with the most probable state to use it here.
How we can combine these probability functions?
That we do. We combine the probabilities. If the probabilities are independent, then we know that the full PDF is a product of the component PDFs. And we maximize the product of the PDF. That is the same as minimizing the log of the PDFs. And log of a product, that is the sum of products. That's how we get from the PDFs down to here. So because sum of x minus, so we've got the sum of the exponent of the background PDF plus the observation PDF. Unless the model are out of here, but we can do that as well. But just let's leave this out of consideration for a moment. So it is maximizing the probability boils down to minimizing sum of the exponents of the probability in this case. So that is what we end up with when we minimize this function here. So it is x minus xp, that's the deviation from the background, weighted by the error covariance matrix of the background, plus h of x, which is observation operator acting on your state, minus the observation, squared, weighted by your observation error covariance matrix. So this is, we could have started here. This is, this is, as I said, this is as I said, this is least square method. I just want to give you, you can look into this further if you're interested. I just want to give an indication that for any kind of, let's say, cost function, anything you write up here, it has consequences for your assumed PDF. Even if it's not a big practical difference, but it's just good to be aware of this connection.
Does anybody want to break before lunch? Or?
Yes.
Yeah, you can go on the.
What do you think, Sasha? What, do we have a break and then before lunch and then continue and then go to lunch afterwards?
It's
I mean,
too
it's
much
too
time.
early.
Well,
We
So
can
that's
lunch
okay.
Lunch is,
sometime after 12:30.
lunch is 1 hour, right? So
Yes.
12:30.
Yes.
So make a 5-minute break and continue and then.
Yeah.
I'll try to get on with this quickly.
Yeah.
Because we can discuss everything in detail later.
Just a 5 minutes break.
Yes,
so
yeah.
we can.
Yeah, let's make a 5-minute break and then
Yeah.
Continue.